Hi there, mathematicians. It's Miss Johnson, and today we're going to continue to look at probability. Today we're going to be looking at compound events and what makes an event independent versus dependent. So far, we've learned all about simple probability, where one event is happening. So compound probability is where two or more things happen. Two or more events happen. Sorry, my handwriting is not neater on this. But make sure you're taking your notes too, okay? It's important. Make sure you put your date. All right, so independent events are events that don't affect each other. So they're completely independent. Think about what the word independent means, right? Like when you turn 18 or when you turn 21, you're supposed to be an independent adult, right? You're not supposed to have to rely on anybody. You can do what you want. You're independent, right? So an independent event is not affected by any other event. Okay, let me give you four examples. Say we have a spinner and we spin the spinner. Well, that first spin of us getting a yellow, it doesn't affect our second spin, right? We can spin it and we can get any of the three colors. Just because we got yellow the first time doesn't mean we won't get yellow again, right? So each spin is independent of the other spin. Just like if we flip a coin. If we flip a coin, sorry, this was not supposed to have 12 on it. Supposed to just have 1. There we go. So if we flip a coin, right, that flip that we just did is not going to affect the second flip, right? I can get heads or tails at any time. One flip does not affect the second flip. Independent event. Rolling dice is the same way. If I roll this dice and I get a 1 the first time, well, the second time I roll it, it's not affected by what I got the first time. I could get a 1 again, or I could get any other number. Just like if I roll 2 dice, what happens on the blue dice is independent of what happens on the pink dice, right? Die. So what happens on one doesn't affect the other. The events are independent. Okay, they don't affect each other. Okay, so for our definition for independent events here, that's what we're going to write. One event doesn't change the other event. And the examples we can use for that would be like if we spin a spinner, if we flip a coin, or if we roll dice. Completely independent events. Independent events could also be like say that your teacher's going to give you candy and you pick out a bag of Skittles, but you don't want the Skittles, so you put the Skittles back. So the probability of you picking something the second time didn't change because you put the Skittles back. Okay? But dependent events, it does matter. So just like that little example I gave about the candy, right? So if there's 10 candies in the bag and the first person in the class gets a candy, what's in the bag has now changed. So the probability that the second person gets is going to change because now there's only 9 candies and not 10. Okay, so let's try to take a look at that a little bit more closely. Okay, so we have 2 circles here. They're exactly the same. We're going to do an example with an independent event and an example with a dependent event. Okay, so let's say we're going to pull out 2. We're going to pull 2 chips. And we want to know what the probability is of pulling out a red and then the second one also being red, but we're going to put the chip back. after we draw it. Okay, so we're going to pull it out and then we're going to put it back in. Okay, so what's the probability right now when we look at our circle, right? What is the probability right now that we will get I guess I probably shouldn't have drawn that circle like that, huh? Oh well. So what's the probability that we will get a red? Yeah, the probability is 2 out of 5. The probability is that we'll pull a red is 2 out of 5. So we're going to pull it out, right? So if we pull it out and we're going to put it back in, has our circle changed? No, it's the same. So what's the probability that we'll pull a red again? Well, the probability is, again, is 2 out of 5. Okay, and so when we multiply that, it's going to be 4/25 that we'll pull a red the first time, and then we'll pull a red the second time when we put the chip back. Right? But when it's a dependent event, it's different. Right? So same situation, we're going to pull 2 chips. And we want the probability that we're going to pull a red and then a red again. But what's going to be different is we don't replace the chip. We keep it out. Okay? So, what's the probability for the first pull that we're going to pull a red chip? Yeah, it's the same as the top, right? 2 out of 5. All right, so we pull it out and we don't put it back. Do you see how what is inside our circle has changed? Now we only have 4 and only one of them is red. So our probability has changed. Our second probability depends on what happens the first time. So when we multiply this, what's our probability now of pulling a red the second time? It's only 1 out of our total has changed, 4. You see how the second event changed because what happened the first time? That's dependent probability. So when we multiply that across, we'll get 2/20, which is different than what we got the first time of 4/25, because what happened the second time was affected by what happened the first time. So that's an example of dependent probability. Okay, so let's go back to our notes. All right, so our dependent events, the second event changes based on the first event. And we could say here, we could say this. We could change this to depends. Right? The second event depends on the first event. It changes it. Okay, so examples of dependent probability would be like if you have a bag of marbles, or like we just did chips, right? The candy, right? The example of the candy. So if the teacher gives everybody a piece of candy, there's 25 candies in the bag, the first person picks the candy, and then the probability changes for the second, right? So now keep in mind though that these, just because it's a bag of marbles or a box of chips or whatever, just because it's that doesn't mean it can't be independent. It can be independent because if they put it back or if they replace it, then it's independent. Okay, so let's look at this Venn diagram. We're going to put some stuff in this Venn diagram. So hopefully we're all familiar with Venn diagrams. So we know that this part in the middle would be true for all three. This part would just be true for independent and dependent. This part would be true for dependent and simple and independent. And then if it's in the spaces by themselves, it would be only true for that item, right? So hopefully we all remember that and remember our Venn diagram. So something that's the same about simple probability, independent probability, and dependent probability is your questions are always going to ask you, what is the probability? Always. So you can't say, oh, this is going to be independent because it says, what's the probability? Or dependent or simple, because all three of them, the question will say, what is the probability? Another word that all three say is random or randomly. I'm going to put the ly in parentheses because they use those words that they use that a lot, random or randomly. I randomly picked a candy from the basket. Okay, simple probability is different from independent and dependent because in simple probability, only one event happens. But for both independent and dependent, two events happen. But how is independent different from dependent? Do you remember from what we just talked about? Yeah, for independent, the events don't affect each other, but for dependent, the events do. So for independent, the events don't change each other. But for dependent, one event affects the other. So that probability is going to change. Okay, a common word that is used with independent is that something would be replaced. And replace just means to put back, right? And for dependent, they'll say it is not replaced. Or they keep it. Or they don't put it back. Trying to keep it in the circle. Well, independent, they would put it back, right? So it wouldn't change the event. Okay, so some things, I misspelled probability. Look at that. Let me erase that and rewrite it. You rewrite it too if you copied my spelling, because that is not spelled correctly. I am not a very good speller. I think, especially when I'm talking, I really spell bad if I'm trying to spell while I'm talking. All right, so some things will be the same for all three, and some things won't. Some things they have, individual properties of. All right, now let's practice some independent questions and some dependent questions, okay? So we're going to do 3 independent questions, and then we're going to do 4 dependent questions because the dependent ones can be a little bit more tricky. So I'm going to explain these as we go. Okay, so it says Alyssa flips a coin and rolls a number cube. What is the probability that the coin lands on heads and a number greater than 4 is rolled? Okay, so whenever you're doing compound probability, there's a couple things you need to pay attention to. The first thing you have to think is it independent? Does flipping the coin and rolling a number cube, will those affect each other? No, they will not. What happens on the coin will not affect the number cube, so that they're independent. It asks us specifically for the coin landing on heads and then a number greater than 4. So we want the probability that we're going to flip heads and get a number that is, I'm just going to put GT greater than 4. We could actually put the numbers there. Let's do that. What numbers are greater than 4 if it's going to be on a number cube? So 5 and 6, right? So 2 things have happened. We're flipping a coin, we're rolling a dice. So that means we need to have 2 probabilities. So however many things happen in your situation, that's how many probabilities you have to have. So we have two things that are happening. We're flipping the coin and we're rolling the dice. So we have to have 2 probabilities. So what's a probability that we'll flip the coin and it'll land on heads? So we have 1 heads out of 2 possibilities times 5 or 6 is greater than 4, right? So that's 2 things that could happen. That could happen 2 ways for us to get greater than 4 out of 6. Now, I always teach my kids to simplify if they can before they multiply. If not, if your teacher hasn't taught you that, you would just multiply straight across and you would get 2/12, and then you would simplify at the end. And this would be 1/6. So there's a couple ways that you could have simplified, and I'm going to go ahead and show how you would simplify. First, you simplify your diagonals, and you would say 2 divided by 2 is 1, and 2 divided by 2 is 1. And then you would multiply straight across. 1 times 1 is 1, and 1 times 6 is 6. So you end up with the same thing if you simplify after, if you simplify before you multiply. So that was independent. That question was independent because the 2 events didn't affect each other. All right, now let's look at the spinner. James spins the arrow on the spinner shown below twice. What is the probability that the arrow lands on an even number on the first spin and an odd number on the second spin? So, sorry about that. So 2 things are happening, right? He's spinning twice, so we're going to have 2 probabilities. So we're going to have the probability that we're going to land on an even number and then an odd number. For the second one. Okay, so what's the probability that we'll land on even? Well, first I got to figure out how many spots do we have here, right? How many? So we have 1, so there's 12 sections of the spinner, and how many of them are even? I'm just going to highlight them. Remember, even numbers, the ones digit is 2, 4, 6, or 8. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. 8/12, which is even, so that's the probability of getting even. Now, is my second spin going to change because of what happened the first time? No. The probability is not affected, so it's independent. Okay, so how many odds do we have? 1, 2, 3, 4 odd numbers out of 12. All right, I'm going to go ahead and simplify both of these. Whoops. I'm going to go ahead and simplify both of these by 4. So that will be 8 divided by 4 is 2, and 12 divided by 4 is 3. And then 4 divided by 4 is 1, and 12 divided by 4 is 3. You can't simplify any diagonal, so I'm just going to multiply straight across. cross. So 2 times 1 is 2, and 3 times 3 is 9. So the probability of getting an even on the first one and an odd on the second spin is 2/9. All right, our last independent example says Kaylee is starting a puzzle. The puzzle has 15 red, 12 blue, 10 yellow, 7 orange, and 6 green pieces. Kaylee randomly selects one puzzle piece, replaces it. That's important. Replaces it, then chooses a second puzzle piece. What is the probability that both puzzle pieces she selects will be yellow? Okay, so this right here is key for us knowing that it is an independent event because she's putting the puzzle piece back. Okay, so we want to know what is the probability that she's going to pull a yellow and then a yellow. Well, how many pieces are there? Right, we don't know. So what do we have to do? That's right, we have to add up the pieces. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay, so 7 and 7 is 14, plus 6 is 20. So 2, 3, 4, 5, so 50. So altogether she has 50 puzzle pieces. And how many are yellow? There's 10 yellow. So the probability the first time that she pulls will be 10 out of 50. Then she's going to put it back. So it hasn't changed. There's still 50. And it's still 10 yellows. So it'll be 10 out of 50. I'm going to multiply that. But of course, first, we notice that we can simplify these by 10. And so when we simplify, 10 divided by 10 is 1, and 50 divided by 10 is 5. Then we multiply straight across. 1 times 1 is 1, and 5 times 5 is 25. So the probability that she will pull yellow, put it back, pull another yellow is 1/25. Or 1 out of 25 tries. That would happen. All right, now let's look at some dependent probability questions and look how they're different. So Jesus has a bag of marbles. He randomly pulls 3 marbles one at a time without replacing them. So there are some key words right there, right? Without replacing. That's a key word to let us know that this is going to be dependent. What is the probability he will draw a white marble first, then a black marble, and then a striped marble? Okay? All right, so he's not putting them back. So when you don't put them back, you have to pretend like whatever event is happening actually happened. So we're looking for the probability that the first one will be white. So the first marble will be white. So we're going to pretend like that actually happens. So how many white marbles are there? There's 4 out of how many marbles? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 10. So 4 out of 10. So he's not putting it back. So let's pretend like he's getting a white marble. So that white marble is gone. All right, now, what's the probability he'll get a black marble? Well, there's 2 black marbles, but how many marbles are in the bag now? It's not 10 anymore. There's only what? Yeah, there's only 9 now. Okay, so let's pretend like he got a black marble. Okay, so black marble gone. Now, we want to figure out from what's left in the bag, how many will be striped. Or what's the probability he'll get a stripe. So there's 4 stripes out of how many are left? 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 left. So do you see how the probability each time changed based on what happened the first time? Okay, that makes it dependent. All right, let's go ahead and simplify these. You always want to make your math as easy as possible. And one thing that makes it easier is if your numbers are smaller. So that's why we simplify. Okay. There's one more thing that we can simplify. We can simplify any numerator and any denominator. So I see here that I can simplify by 2. 2 divided by 2 is 1, and 2 divided by 2 is 1. And there's nothing else that can be simplified. So we're going to multiply straight across. So 2 times 1 is 2. 5 times 9 is 45 plus 1. I mean, not plus 1. 45 times 1 is 45. So he has a 2 out of 45 chance that he'll pull a white, then a black, then a striped out of the bag. Okay, notice 3 things happened, right? We had 3 probabilities that we multiplied. 1, 2, 3. Okay, so however many events happen, that's how many probabilities you have to have. Just keep that in mind. All right, let's look what happened in Miss Washington's tutoring class. So she has 7 girls. So Miss Washington's tutoring class has 7 girls and 3 boys. She will randomly choose 2 students. I told you that word randomly comes up a lot, right? So she randomly chooses 2 students to do a problem on the Zoom whiteboard. What is the probability that she will choose 2 boys? So what is the probability that she will choose a boy and a boy? So why is this dependent? Well, because the first boy, like it can't be the same boy, right? It's got to be a different boy. They're going to do the problem on the whiteboard at the same time. So it's got to be 2 different boys. So that's why. So sometimes it helps if we draw a visual. So we had a visual of the marbles. Those are G's, by the way. 1, 2, 3, 4, 5, 6, 7 G's and 3 B's. So what's the probability that you'll choose a boy the first time? Well, it will be 3 out of 10. She chooses a boy. So 1 boy is gone. He's been chosen. So now what's the probability? She chooses at random. She'll choose a boy again. Well, there's 2 boys left. Whoops. 2 boys left out of how many children? That's right, out of 9. So, can we simplify? No. All right, so yes, we can. 2 and 10. Sorry. So, what happened the second time was affected by what happened the first time. Our total changed to 9, and the number of boys changed to 2. So let's go ahead and simplify that. And then multiply straight across. So 3 times 1 is 3. And 5 times 9 is 45. So dependent. What happened the second time? Change because of what happened the first time. And remember, when it's dependent, we have to pretend like it happens. Okay, so she did choose a boy the first time. So what would happen the second time to get the boy? All right, number 6. So Mr. Phelps needs 50 cents to pay for the newspaper. He has 6 times 5 quarters and 4 nickels in his pocket. If Mr. Phelps reaches into his pocket and randomly takes out 2 coins, one at a time, without putting either one back. So there's our clue, without putting them back. That's our clue that's going to be dependent. What is the probability that he will select the 2 quarters he needs? Okay, so we're looking at the probability of a quarter and a quarter. Okay, so what's the probability? So there's 5 quarters. So what's the probability? Oh, we got to have the total. All right, so let's add it up. So 6 dimes, 5 quarters, 4 nickels. So that's 10, 15. So he's got 15 in his pocket and he's got 5 quarters. Okay, so he takes one out. We're going to pretend like it's a quarter. So this is going to go from 5 to 4. So I'm just going to do that over here too. That goes from 5 to 4. So my total is not 15 anymore. Now it is 14. So what's the probability that he will get a quarter again? Well, it's going to be 4 out of 14. Oh, I'm so glad we can simplify because I do not want to multiply 5 times 14. All right, so I see I can simplify 5/15. I can simplify that by 5. And that will be 5 divided by 5 is 1. 15 divided by 5 is 3. And then I can also simplify 4 and 14 by 2. So 4 divided by 2 is 2. And 14 divided by 2 is 7. Now I can multiply straight across. That's going to be 2 over 21. So the probability that he'll select the 2 quarters he needs is 2 out of 21. All right, last dependent practice. Jana has 11 new paperback books. 3 of the paperback books, I'll go ahead and write a 3 here on top of that. 3 of the paperback books are mysteries. 3 are science fiction, and the rest are romance. If Jana were to randomly select 2 books from this set without replacing them, there's our key word right there, without replacing them, that let us know it's going to be dependent. What is the probability that the first book selected is science fiction and the second book is romance? So, probability of sci-fi and romance. Okay, so we have 11 paperbacks. 3 are mysteries, 3 are science. So I'm just going to do this. 3 are mysteries. 1, 2, 3. 3 are science fiction. 1, 2, 3. And the rest are romance. So how do I figure out how many are romance? Yeah, we just say 11 minus 6 is 5. So 5 are romance. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So what is the probability that on the first pull that she'll get science fiction? There's 11 books, and how many are sci-fi? 3. So the probability is 3 out of 11. So remember, you pretend like that happened. So she pulled a sci-fi. Now what's the probability she'll get a romance book? Well, there's 5 romance books left. And how many total books left? Right? 11 minus 1 is 10. So the probability the second draw will be a romance is only 5 out of 10. All right, can we simplify anything? Thankfully we can. So we're going to divide this by 5. And we're going to say 5 divided by 5 is 1. And 10 divided by 5 is 2. Can't simplify 3/11ths. Those are both prime. And now we can multiply straight across. So 3 times 1 is 3. And 11 times 2 is 22. So the probability would be 3 over 22. Okay, so hopefully you learned some key things that distinguish between an independent and a dependent problem. Mainly the independent, remember, the first event does not affect the second event. And they replace or they put back items. But the dependent events, they do not put the item back. Without replacement is a key word there, or they keep it out. Okay, putting back, right? Okay, so that's independent and dependent events. I hope you learned a lot. Now it's time to practice.